we were talking about last week. So for the standard normal distribution, where the by standard I mean that the mean is 0, the standard deviation is 1. We had the density function we called phi, 1 over the square root of 2 pi e to minus x squared over 2. And then we talked about the cumulative distribution function. It's called capital phi, whose value at some number, say, z. Well, so this is the cumulative distribution function. It's the probability that the random variable, call it capital Z, has value less than or equal to this number. And so, of course, we get that by integrating the distribution function up to z of the 5x. Well, we talked about calculating probabilities. Let's look at a problem where we're given the probability and we want to calculate one of the other numbers. Assume we have a random variable, as always called capital Z, that has this distribution. We want to find a number, call it little z, a z value here. It's the probability that the random variable in absolute value is less than or equal to z will be 95%. That is, we're given the probability. It's 95%. We want this number, little z. Well, step 0, before doing anything, is to draw the picture. Okay. So we know what the density function looks like. The graph of little phi. And, well, the total area under the curve, of course, is 1. And we want something that's not that far below 1. We want a number z. So this probability, the probability that the distance between z and 0, the distance between z and its mean, is no more than the number we're looking for. So we could write that the random variable can be between minus little z and plus little z. But that probability has to be 95%. Well, so back to drawing the picture. The thing that's 95% is this shaded area between minus z and z. And what we're looking for is the number. Well, we have a table for the cumulative distribution function. So It would be nice if we knew what phi of z is supposed to be. Well, we can get that from this picture. Phi of z is not 0.95. Phi of z would be the area from z all the way down to minus infinity, including this left-hand tail. So that's more than 0.95. Yeah? Well, what is it? We've got 0.95 here. That means the other 0.05 is made up by the two tails. And because it's symmetric, the two tails are the same. That is, the left-hand tail has got to be 0.025, and the right-hand tail has got to be. Because the two tails together have to add up to the missing 5%. And because it's symmetric, it's 2.5% each. So phi of z that's the area under the curve from z all the way down to minus infinity. Well, it's 95% here and another 2.5. In other words, we're looking for a number, phi of which is 0.975. So we look in our table, or we ask our calculator. We look for a number, phi of which would be 975, and we find such a number. It's 1.96. So by reading our table backwards, that is, what would you have to put into the table to get 97.5 out? And the answer is 1.6. Well, so it's almost 2. So the probability that z is within 2 standard deviations of its mean would be a little bit more than 95%. Well, but that's not what we're going to talk about today. We want to look at normal distributions where maybe the mean is not 0. Maybe it's something else, or the standard deviation perhaps is not 1. So we'll start off from the standard normal distribution. So z has mean 0 and standard deviation 1. And we know a lot about it. Now let's look at a different random variable. Call it x. 2z plus 3. Okay, it's a new random variable. Here's 3 things we can say about x. We know what the expected value is, right? Try that again. We all know what the expected value of x is, right? Okay, 3 things. 1, the expected value of x. Well, by property of the expected value, the expected value of the sum is the sum of the expected value. So expected value of 2z plus the expected value of this constant random variable. When we double a random variable, that doubles its expected value. Well, big deal. Its expected value is 0. So Doubling it doesn't do that much. So we have the expected, twice the expected value of z. That's still 0. Because z has the standard normal distribution. Its mean is 0. Plus the expected value of a constant. Yeah, so x has expected value 3. What's the variance of x? Remember about variance? And standard deviation of x. Well, the variance of x is 4. As we're supposed to know from, I don't know, weeks ago, if you have some random variable, don't call it x or z, so we'll call it y, and you multiply it by some constant, say a, that multiplies the variance by a squared. And if you add a constant to it, that doesn't affect the variance at all. The variance gets multiplied by an a squared. Okay. And it's a formula that you all knew once a time, but it wasn't that long ago. And in the case of, so for the variance of z, we know is 1. The standard deviation is 1. The variance is 1 squared. So with the variance of 2z plus 3, that's going to be 4 times the variance of z. So that's 4 times 1. So the standard deviation of x standard deviation is 2. Okay, the third one is a little more work. We want the density function for x. We know the density function for z, right? It's right up there on the board. What we want is the density function for x. And the way we're going to find it is to write down its cumulative distribution function and take its derivative, because we know the density is the derivative of the cumulative distribution function. So first, we'll get the cumulative distribution function for x. Call it capital F. That's what we usually call it. The probability that x is less than x. Now, going back to this equation we started with, if we solve this equation for z, z is x minus 3 over 2. And in fact, we're going to go back and forth between these two equations all the time over the next few days. Like now. I'm going to do something that we call standardizing this random variable x. The event, capital X less than or equal to little x, that's the same event as x minus 3 less than or equal to little x minus 3. And I mean, all we did was subtract 3 from both sides of the inequality. That's an equivalent inequality. And it's the same as, now we're going to divide both sides by a number, namely the standard deviation, 2. And again, it's an equivalent inequality. So it's the same event, same probability. And the reason for doing that is that this is z. And we know a lot about z. We know its density function, the works. It's this is the cumulative distribution function for z, but at the point x minus 3 over 2. So if we write it out as integral, it's the integral from minus infinity up to x minus 3 over 2 of the density function phi. Better not use the letter x for the variable of integration, better use something else. Well, we have a formula for the cumulative distribution function for x, but that wasn't the problem. We want the density function. The density function for x. Called little f. That's what we always call it. Yeah, but we know the density is the derivative of the cumulative distribution function. And we have the cumulative distribution function in front of us. We take its derivative. Using, of course, the fundamental theorem of calculus that says the derivative of an integral is the function you're integrating. Okay, so we calculate this derivative. We're using fundamental theorem calculus. Well, if it were just integral from minus infinity to x, we'd have just phi of x. But we have the integrand evaluated at that upper limit of integration. And then applying the chain rule, we take the derivative of x minus 3 over 2, which is a half. So here's the density function for capital X. It's we have that formula for phi, and it's evaluated at this point, and there's this 1/2 here. So we have 1 over 2 times the square root of 2 pi. That is, this half gives us this 2 down here in the denominator, times e to the minus x minus 3 over 2 squared. The density function for x. Well, which we get by differentiating the cumulative distribution function. And yeah, got to use fundamental theorem of calculus from Math 3A. Well, even better, let's generalize this so it'll be useful in other problems later. Suppose instead of 2 and 3, we had some other numbers, say mu and sigma, letters not chosen quite at random. So where we're still assuming Z has the standard normal distribution. In fact, we'll pretty much use the letter Z only for random variables with the standard normal distribution from now on. And okay, instead of 2Z plus 3, what if we take sigma times Z plus mu? Where sigma and mu are some constants. And the reason I choose those letters will be probably, well, it's probably already obvious why I want to use those letters. So before we used 2 and 3, but what if we generalize? And this equation is equivalent to the equation we get if we solve for Z. Z would be x minus mu over sigma. Then some things we can say about x. Looking at it, we know what the mean of x is. Right? The expected value of x is sigma times, well, right, sigma times 0, sigma times the expected value of z, but z has mean 0, plus the expected value of this constant. Expected value of x is mu, that's why I use the letter mu. And standard deviation is sigma, that is, the variance of x is sigma squared times the variance of z. In other words, it's sigma squared times 1. So x has standard deviation sigma. That's why we use the letter sigma. And now we copy over the calculation of the density function, or at least mentally we count, but with 2 replaced by sigma and 3 replaced by mu, and we get the density function for f. Then density function for x is the function f of x, 1 over sigma square root of 2 pi e to the minus, okay, we have x minus mu over sigma squared. Exactly as in the center board, but with 2 and 3 being these letters. And instead of that 1/2, we get a 1 over sigma coming out. And we get the integrand evaluated at x minus mu. Well, it's a wonderful equation. We hardly ever use it directly because this is not a function that's easy to integrate. But this random variable x is said to have the normal distribution, not the standard normal distribution, but the normal distribution with mean mu and standard deviation sigma. Well, so we've branched out. We're not just looking at the standard normal distribution where the mean is 0 and the standard deviation is 1. We're looking at normal distributions with other means and other standard deviations. And we'll want to use this normal distribution in a variety of situations. First, let me just draw some pictures. Of the density functions. Well, the density function for z, where z has we know a lot about it. It's got those inflection points at 1 and -1. Well, we talked about it last time. What if we take 2z? What is the density function going to look like? Well, it's going to have an inflection 2z. The standard deviation is going to be 2. Well, that's going to spread things out some. So that's 1, 2 is around there. Its value at 0 is a little smaller because we've got this 1 over sigma here. Total area, it's a density function. Total area is still 1, but it's more spread out. What if sigma is a half? The density function for 1/2 z, well, things are bunched more tightly around 0. Z over 2 still has mean 0, but the standard deviation is a half. Yes, it's going to pull things in. And the density function for z plus 10, well, that's going to be in this picture out here somewhere. Say that 10. Z plus 10 still has standard deviation 1, of course. Yeah, but the mean has been moved forward. Well, let's calculate a probability in this setting. And then we want to do the same problem, but in the other direction. Again, what if we're given the probability and we want one of those other numbers? Well, which one? Okay, well, first things first. Let's calculate a probability. So here's a problem. Assume x has normal distribution with mean 3, standard deviation 2. So that's going back to that situation up there. We want the probability that x is less than or equal to 4. Well, how not to do it? We're not going to do it by integrating its density function from -infinity to 4. That would indeed give this probability, but it's not feasible to integrate this function. So what are we going to do? Well, step 0, before we even start work, is to draw the picture. The density function for x Yeah, the mean is 3 and the standard deviation is 2, so we know what the density function looks like. It looks like this. And we need 4 in this picture. 4 is 4. And we want the probability that x is less than or equal to 4. That is, we seek that shaded area there all the way down to minus infinity. We're ready for step 1. We want this area. Well, there are 2 ways to go. You could go to a normal distribution calculator on the web and just punch in these numbers, the mean, the standard deviation, and the upper limit. And ask it what the probability is. And there's a zillion normal distribution calculators on the web. A search engine will direct you to a bunch of them. For that matter, our homework page has a link to one of them. Or, if we don't happen to have web access with us, we'll work it out. And the first thing we have to do is to standardize the problem. Convert it from x to z. That is, we have to convert the problem to something with the standard normal distribution because our table is for the standard one, not for x. So this thing we're after, the probability, that would be the same as. And now we subtract the mean. The mean is 3 from both sides of the equation. That's still the same event, right? Equivalent inequality. And we divide both sides of the inequality by 2 because 2 is the standard deviation. And the reason we do that is that now on the left we have a random variable with the standard normal distribution. And so we'll call it z, as we always call it. Because if x is normal and with this, then x minus mu over sigma will be z. So we want the probability that, that z is less than or equal to 1/2. In other words, what we're after is nothing but 5/2. Well, now we have a choice. We can ask our calculator what 5/2 is. Assuming if you have a statistical calculator with a phi button on it, you ask it for 5/2. Or if you don't happen to have access to a statistical calculator, we use the table on page 919. Which says 5/2 is 0.6915. About 69%. End of the problem. The probability we're after is about 0.6915. And this is the method. We'll draw the picture. We convert it to z, because we know we have a table for z, or a button on our calculator for z. And then we figure out the probability. Now, what about what about doing it backwards? What if we know the probability? This problem that I'm just erasing, I guess, is the one where we're given the probability, 95%. And what we want is something else. Well, in general, suppose we have a random variable x that's normally distributed. And we're interested in the equation the probability that x is between a and b that's what comes up here. A is minus infinity, b is 4. Well, there's 5 numbers floating around here. There's A, there's B, and there's C. And then, less sort of hidden in this equation, there's the mean of x and the standard deviation of x. So there are these 5 numbers here. If we know any 4, we can find the 5th one. In this problem, we were given mu and sigma and A and B, and we wanted C. But let's do one of the homework problems is we're solving for sigma. Actually, solving for mu is not, it's kind of a nuisance, but we can do it if we have to. Let's do the following problem. Solve for A. Back to this random variable. Has normal distribution. Its mean is 3. Its standard deviation is 2. Only now we're going to solve for A. We want to find a number A. The probability that x is between A and 3 is 30%. That is, of these 5 numbers, we know 4 of them. We know mu, we know sigma, B is 3, C is 0.3. We want A. But the method is the same. In outline, step 0, we draw the picture. Well, we know what the density for x looks like. Draw it again. And we're looking for a number A. We're not sure where it is in this picture, but something is 0.3, and we want to put in our picture what that something is. It's this 0.3 is this probability. It's the area under the density curve from 3, which happens to be the mean, down to this unknown number A. shaded area right there, that's what the 0.3 is. Well, there is such a number. If we change the 30% to 60%, there would be no solution. Because we're starting to mean here, 3. Even if we went all the way down to minus infinity, we'd only get 50%. We couldn't possibly get 60. Okay, but that's not the situation. Yeah, there will be a number there that gives us 30%. We want to find it. How? Well, on to step 1. Standardize. That is, we have this equation. We want to convert from x to z. This 0.3, the 30%, that's the probability that x is between a and 3. And this event is the same as. And now we standardize. We subtract the mean. We divide through by the standard deviation. So we'll subtract the mean from each term. So we have an equivalent inequality. It's still the same event. And we divide through by the standard deviation, which is 2. And the reason we do that is that now we have the standard normal distribution. So the previous picture standardized. We're looking for a number we don't know, a minus 3 over 2. It's clearly a negative number. And that 0.3 is now moved over to this area. We'd like to know what that number is. Well, it's a negative number. It'd be a little more convenient to reflect this picture in the y-axis so that we're looking at a positive number. Particularly if we're doing it without a statistical calculator. The mirror image of this picture, now the area is over here. And it's still 0.3. And this number in the reflection is the negative of the previous number. It's 3 minus a over 2. The negative of a minus 3 over 2, because we've taken the reflection. Minus a over 2, that's, we know from the picture, that's some positive number. And if we knew phi of that, we could start using our table. We do know phi of. We look at that picture. What's phi of 3 minus a over 2? Right, it's 0.8. Phi of this, it's the area under the curve from here down to minus infinity. There's 0.3 here, and then this half is half. 0.3 plus. We're looking for a number, phi of which would be 0.8. And if we're phi of what would be 0.8? Well, if we're using our table on page 919, we see what comes closest to 0.8. And we find the closest we can get in our table is 7996. The probability entries in the table, this is the closest one to 0.8. And it comes from, that's phi of 0.84, our table. Now, there are ways to be a little bit more accurate. Well, a statistical calculator would be more accurate. We could use linear interpolation, which is sort of an old-fashioned technique for getting a little more accuracy. We're not going to bother with those. We will take 0.84 because that gives us the thing closest to 0.8. Well, we're not done with the problem yet. But this number we're looking for, 3 minus a over 2, turns out to be 0.84, approximately. An equation we can then solve for a and we'll be done. So 3 minus a is twice that, 1.68. So a is 3 minus 1.68, 1.32. Back in the original problem, a turned out to be 1.32. The point is, in that equation where there are 5 things floating around, knowing any 4 of them will let us find the 5th one. Okay, got to stop for today. If you're a Tuesday person, remember that you're turning in your homework now.